Chapter 6 is a very important chapter for us. We're going to be using a lot of the material that we learn in this chapter throughout the rest of the year. So make sure if there are things that you don't understand that you get help right away. Chapter 6 is focusing on using the concept of standard deviation as a ruler in order to compare data sets. And we also get introduced to a very important model referred to as the normal model. So today's focus, though, is specifically on the concept of using the standard deviation as a ruler. So let's look at some information. What could you do to compare, for instance, a male athlete and a female athlete in a marathon? Because when a marathon occurs, everybody's running at the same time, but the men and the women are separated because there are differences in gender. So are there ways to compare them? What about how could you compare scores that you received on a science test with a score that you received on a history test? Two very different subjects, not easy to compare. Or better yet, what if you wanted to compare the performance of someone who performed in both the long jump and someone who performed in the 50-meter dash? Can you compare those? Well, you've probably heard the saying, you can't compare apples and oranges. Now we can. This chapter gives us ways to compare two different things that really we shouldn't be comparing. All sets of data that you collect, you can calculate a mean and a standard deviation for them. So because every data set we are able to calculate those two scores, we can use standard deviations to compare values that would normally not have any standard units to be able to compare. So to compare data using standard deviations, we convert the values into standardized values denoted by what's called Z, or also called Z-scores. So we have this very important formula right here, and I'm going to do some labeling. So obviously Z stands for Z-score, or standard score. X is your one data value that you want to convert into something comparable. X bar is the mean of your data set, and S is the standard deviation of your data set. So this little formula, I will tell you right now, you will need it on the test. It will not be provided. You must have this formula memorized. But by the time we use it as much as we are going to in this chapter, you should have it memorized anyway. So some more information about these Z-scores. We refer to them, the formal term for Z-scores is standardized values. You won't hear me use the word standardized values. You will simply call them Z-scores. One important thing about these, they have no units. That's what makes them comparable. So a Z-score simply measures, and this is important, how many standard deviations a value is from the mean. The definition of a Z-score is how many standard deviations a value is from the mean. Don't be surprised if that pops up on a test question. So a negative Z-score simply means that the value is below the mean, and a positive Z-score means the value is above the mean. Now, the further a Z-score is from 0, because 0 is the middle, the more unusual or extraordinary the data value is. So when you're asked which one is more extraordinary or compare them, the further it is from 0, the more unusual or extraordinary the data value is. So here's how they work. Let's look at our first example. Consider the 3 athletes' performances shown below in a 3-event competition. Each person placed first, second, and third in an event. The question is, who gets the gold medal? In other words, who turned in the most remarkable performance of the competition? So let's take a look at some information here. So competitor A in the 100-meter dash had a 10.1 seconds. Shot put was 66 feet. long jump 26 feet. Competitor B, 100-meter dash was 9.9 seconds. Shot put 60 feet, long jump 27 feet. Competitor C, 100-meter dash 10.3 seconds. Shot put 63 feet, long jump 27 feet 3 inches. And then at the bottom it gives you the mean and the standard deviation for each event. So the 100-meter dash had a mean of 10 seconds, standard deviation of 0.2 seconds. The shot put had a mean of 60 feet, standard deviation of 3 feet. And the long jump had a mean of 26 feet and a standard deviation of 6 inches. So for instance, each person placed first, second, and third in an event. If you look at the 100-meter dash, the faster you are, the better. So the winner for the 100-meter dash was person B. The shot put, the further you throw, the better. So person A was your winner. The long jump, the further you jump, the better you do. Person C jumped the furthest. So they each had a high point, but they each had low points. So we need to figure out which person overall did the best. This is where z-scores come in. It takes all of these data values that have some units of seconds, some feet, some inches, and it makes them all comparable. So what we're going to do is we're going to go through in these little blank boxes and we're going to convert each data value into a z-score. So remember, the formula is x minus x bar divided by standard deviation. X is each one of the data values for the competitors. X bars are your means at the bottom, and SD is your standard deviation at the bottom. So the first person, to convert this into a z-score, we're going to take 10.1, because that's the data value, minus the mean, which is 10, divided by the standard deviation of 0.2. And if you put that in the calculator, I end up with 0.5. We're going to do the same thing for B and C. The 10.1 becomes a 9.9 minus 10 divided by 0.2. See, very easy formula to use. Put that in the calculator. By the way, when you're typing this in the calculator, 9.9 minus 10, hit enter, then divided by 0.2. That's how you make sure you get a correct answer of negative 0.5. And finally, 10.3 minus 10 divided by 0.2 comes out to be positive 1.5. So we're going to do the same thing with the shot put. Now we have some new numbers. Our new mean is 60 and our new standard deviation is 3. So 66 minus the mean of 60 divided by the standard deviation of 3. Put that in the calculator, you get 2. 60 minus 60 divided by 3, you should get 0. And 63, take away 60, divided by 3, you end up with a 1. Now, we have a problem with the long jump. You cannot have mixed units. You cannot have inches and feet. So we have to do a couple of conversions. Let's do the easy conversion first. 6 inches is how many feet? Well, there's 12 inches in a foot, so 6 inches is 0.5 feet. So now this other one. Let's start with just the 3 inches. 3 inches out of 12 inches, 3 divided by 12 is 0.25. And then you just put the 27 in front. This is 27.25 feet. That's important because it has to be converted to feet in order to use the formula. So now let's go back to what we were doing. Data value 26 minus the mean of 26 divided by 0.5, you get 0. Data value 27 minus 26 divided by 0.5, I end up with 2.5. And data value 27.25 minus mean of 26 divided by 0.5, I end up with 2. Now, we have to find a way to put them all together. Here's the issue. The shot put and the long jump, higher is better. But the 100-meter dash, lower is better. So this negative 0.5 for person B for the 100-meter dash, that's technically a good thing. But if we add it with the other numbers, it's not being treated like a good thing. So what we're going to do is we're going to take the shot put and the long jump, and we're going to add those two together. Then we're going to subtract the 100-meter dash because that one lower is better. So for instance, person A, their positives would be 2 plus 0, which is 2, but we're going to take away 0.5 because they did worse in the shot put, or in the 100-meter dash. So 2 take away 0.5 is 1.5. Person B, 0 plus 2.5 is 2.5, but by subtracting a negative, we're really ending up adding 0.5. That helps them, and that gives them, I'm sorry, I had a number wrong, didn't I? I need to fix something real quick. This should not have been a 2.5. Hopefully you caught that and realized that that should have been a 2. There we go. So now we are back to our adding 0 plus 2 plus another 0.5 is 2.5. And finally at the bottom, 1 plus 2 is 3. But you got to take away that 1.5 because he did the worst. 3 take away, wow, I'm really messing up more than 1. I apologize. This 2 here at the bottom should have been 2.5. I flip-flopped them when I was looking at my answers. So let's try it again. 1 plus 2.5 is 3.5. Take away 1.5 is 2. So if we had to assign medals, your gold would go to the person who had the highest total. That would be person B. The silver would go to be the person who has the next highest. That would be person C. And your bronze would go to the person in third, which would be player A. So that's how you use z-scores to compare. Now we're going to use the data below and a graphing calculator to compute the following statistics. Then we're going to add 4 to each of the original data values and recalculate the statistics. Finally, we're going to multiply each of the original data values by 3 and recalculate the statistics again. So this is where you need a yellow calculator, and you're going to use the skills that we learned last in chapter 4. So that's where we went to stat and we went to calc and we edited it and we put all of the data in the first column. So pull out your calculators, press stat, calc, enter, and then type in all of these values. Pause the video and then start it back up when you're done. Now that you have all of your data in, you press stat again. This time you arrow right to the calculate menu and you press enter until you get your calculations for your data set. So the original data set, I ended up with a mean of 7.6. A standard deviation, remember that's the S, this was the X bar. A standard deviation of 4.45. Then you got to arrow down. The median was 7. Now the IQR, you need to find that by taking Q3 minus Q1, and I end up with 8, a maximum of 15, and a minimum of 1. So now we're going to repeat exactly what we did, but you're going to add 4 to each original data value. So you're going to go back to stat, enter to edit, and so instead of 1, you're going to make it 4. Instead of 3, you're going to make it 7. Instead of 4, you're going to make it 8. Until you get to 15, and instead of 15, it's going to be 19. Do that. Pause the video. Okay, now that you've done that, you're going to go stat, arrow over to calc, and hit enter for option 1. Your new X bar changes to 11.6. Your standard deviation stays 4.45. Your median, if you do, you end up with 11. Your IQR, if you take Q3 minus Q1, I get 8 again. My maximum went up to 19, and my minimum went up to 5. So now, our final step is to multiply each original data value by 3. So, stat, enter to edit. Instead of 1, we're going to put in 3. Instead of 3, we're going to put in 9. Instead of 4 is 12. And all the way up to 15 changes to 45 because you're multiplying by 3. Pause the video. Okay, now all you have to do is press stat, arrow over to calc, and hit enter. My mean changes to, my mean changes to 22.8. This time my standard deviation changes to 13.35. My median changed to 21. My IQR, if you do Q3 minus Q1, I end up with 24. My maximum is now 45, and my minimum is now 3. So I want to point out some things. When we did the addition, there were 2 things that didn't change. And that was your your standard deviation and your IQR. They didn't change when we added. Here's why. When you added to everything, a data set that went from 1 to 15 simply moved this distance that was this wide, it simply moved over to 4 and up to 19. That width didn't change. And if you remember, standard deviation and IQR tell you how spread out the data is. But when we multiplied, the 1 changed to a 3, but then the 15 went way over here to 45, and that data stretched out. So multiplying, everything changed. This leads me to my next slide. When you're adding or subtracting all of the data values by the same amount, the following things will change. The mean, the median, the minimum, and the maximum change by adding or subtracting the exact same amount that you did to the data values. And also in this list, you can add to it Q1 and also Q3 because they also change. But what doesn't change are the IQR and the standard deviation. When you multiply all of the data values by the same amount, everything changes. The mean, the median, the minimum, the maximum, the IQR, the standard deviation, Q3 or Q1 and Q3 all change by multiplying by that same amount that you did. So that's going to be important. You're going to have that pop up on your homework. It's going to ask you what changes. We're going to apply this to some thinking. Remember, IQR and standard deviation are only multiplying. So let's apply this to some examples. Suppose the class took a 40-point quiz. Results show a mean of 30, a median of 32, IQR 8, standard deviation 6, minimum 12, and maximum 40. What happens to each of the statistics if I decide to weight the quiz as 50 points and I add 10 points to every score? So the key there is you are adding 10 points to every score. Keyword is add. So, will the mean change? Yes. We're going to add 10 to 30, and we're going to get 40. Will the median change? Yes. We're going to add 10 to 32 and get 42. 42. Will the IQR change? No, that only changes by multiplying. It stays 8. Standard deviation, only multiplying. It stays 6. Minimum, yes, we're going to add 10 to make it 22. Maximum, yes, we're going to add 10 to make it 50. Okay, new plan. Now I want to weight the quiz as 80 points. So I'm going to double each score. And what does doubling mean? Hopefully you know that doubling simply means multiply by 2. So now we are multiplying. The mean, it started at 30, double it, it becomes 60. Median, started at 32, double it, it becomes 64. The IQR, does it change? Yes, it does. We are multiplying. It goes from 8 to 16. Standard deviation, same thing. We are multiplying. It goes from 6 to 12. The minimum, it goes from 12 to 24. And the maximum goes from 40 to 80. Now I'm going to do two things. I want to count the quiz as 100 points. I'm going to double everything. And so our first step is double each score. And then I'm going to add 20 to each score. So for doubling, we already established in part B that they all changed. But adding 20, not all of them. Remember, no IQR and no standard deviation. So I'm going to use the numbers from B because that's already doubled. But when I get to the IQR and standard deviation, I am not adding 20. So the mean, doubled with 60, add 20 is 80. The median, doubled with 64, add 20, you're at 84. IQR, doubled is 16, stays 16. Standard deviation, doubled is 12, stays 12. Minimum, doubled is 24, add 20, it jumps to 44. And the maximum, doubled is 80, add 20, we jump to 100. So just make sure that you know what kind of math you are doing. Let's look at another one similar to this. Each year, thousands of high school students take either the SAT or the ACT standardized tests used in the college admissions process. Combined SAT, math, and verbal scores go as high as 1,600, while the maximum ACT composite score is only 36. Since the two exams use very different scales, comparisons of performance are difficult. A convenient rule of thumb is to find the SAT score, you take 40 times the ACT score plus 150. That is, multiply an ACT score by 40, then add 150 points to estimate the equivalent SAT score. An admissions officer reported the following statistics about the ACT scores of 2,355 students who applied to her college 1 year. Find the summaries of equivalent SAT scores. Now remember, here you have two actions. You have multiplying and adding. Multiplying applies to everything. Adding does not apply to the standard deviation and the IQR. So, you will need a calculator because these numbers get big. The minimum, we get to do both. So you're going to take 40 times the 19 plus 150, and you get 910. The mean will go across. The mean of 27, we get to do both. 40 times 27 plus 150, I get an average of 1,230. Now this is standard deviation. He is special. He only likes multiplying. 40 times 3 is 120. Q3, he likes both. So we're going to do 40 times 30 plus 150, and I get a Q3 of 1,350. The median likes both. So 40 times 28 plus 150, I get 1,270. The IQR, he is special. He only likes multiplying. 40 times 6 is 240. So just stop and think about adding. Does not like IQR and standard deviation, but multiplying likes everything. So we know that the mean score on the stats exam was 75 points with a standard deviation of 5 points. Gregor's z-score was -2. I gave you his z-score. How many points did he score? This is a working backwards. So think about your formula. Remember, it's z-score equals x minus x bar divided by s. So his z-score was -2. We don't know x. X is his data value. Minus the mean, because x bar is the mean, is 75, divided by s, standard deviation, which is 5. Now you're doing some basic algebra. You need x by itself. Well, to get x by itself, I'm going to get rid of this division. The opposite of dividing is multiplying by 5 on both sides. 5 times -2 is -10 equals x minus 75. Then I'm going to add 75 to both sides to cancel that. So I end up with x equals -10 plus 75. Gregor got a 65 on his test. He didn't do very good. So that's a simple working backwards problem. Now, here's where z-scores again can help you with comparison. A town's January high temperature averages 36 with a standard deviation of 10, while in July, the mean high temperature is 74 and the standard deviation is 8. In which month is it more unusual to have a day with a high temperature of 55? That's the one data value. But we need to compare that data value in January compared to July. This is where z-scores come in. We're going to use that number for both months and we're going to turn it into a z-score. So the data value is 55. January's mean was 36 and January's standard deviation was 10. So 55 minus 36, hit enter, divided by 10, I get 1.9. Same thing for July. Our data value is 55, but July's mean is 74, and July's standard deviation is 8. 55 minus 74, enter, divided by 8, I get -2.375. So which day would it be more unusual? Remember, we talked about z-scores. Unusual means further from 0. So the number that is further from 0 is your July month, because that is much further from 0 than 1.9. So July would be the month that it would be more unusual to have a high temperature of 55. So let's look at our last example. Anna, a language major, took final exams in both French and Spanish and scored 83 on each. Her roommate Megan, also taking both courses, scored a 77 on the French exam and a 95 on the Spanish exam. Overall student scores on the French exam had a mean of 81 and a standard deviation of 5. The Spanish scores had a mean of 74 and a standard deviation of 15. To qualify for language honors, you must maintain at least an 85 average for all language courses taken. So far, which student qualifies? Well, averages are very simple. Add and divide. So Anna had an 83 plus an 83, because she got 83 on both, divided by 2. Well, that obviously means she had an average of an 83. Whereas Megan had a 77 plus a 95, and divide that by 2, and you get 86. So who actually qualifies for language honors? That would be Megan. She has the 86. That meets the requirement of at least an 85. The problem is, which student's overall performance was better? This is where we want to convert to z-scores so that we can compare apples and oranges. So let's start with Anna. So let's do Spanish first. So Spanish's z-score, she had an 83 minus the mean for Spanish was 74 divided by the standard deviation for Spanish was 15. I end up with 0.6. Her French z-score, she also had an 83, but The mean for French was 81, divided by a standard deviation of 5. And so I end up with 0.4 on that one. So those are her two conversions. Then we have Megan over here. So Megan's Spanish score was a 95 on Spanish. Take away 74 for the mean, divided by 15. I end up with 1.33. And her French z-score, she had a 77 on French, minus 81, divided by 5. She didn't do well in French. She was below average. That's a negative 0.8. But we want to know who did overall better. So what we're going to do is we're simply going to add those numbers together. So 0.6 plus 0.4 comes out to be 1.0. 1.33 plus negative 0.8 comes out to be 0.53. So Megan was the only one that qualified for honors, but Anna is overall the better performer. And that's how we use z-scores to compare data values. So that's what your working class is going to be all about.